Hello, welcome back. This is mini lesson 2 for chapter 2 of our basic chemistry chapter. This lesson is going to cover atomic structure and chemical bonding and a little bit of chemical reactions at the end. So let's get started. So the first thing I wanted to talk about is kind of showing you the periodic table. Now this isn't a chemistry class, so we're not going to dive in too deep with chemistry, but we do have to understand some basic ideas of atoms, chemical bonds, and how they kind of work with each other, because that's going to help us in the cell biology and some of the physiological processes. So when we talk about matter, right, so matter was anything that has mass and takes up space. All states of matter, all kinds of things are made up of elements. And so this is a table that organizes all of those elements. In living systems, we really only go up to about number 20. So these, and we don't really do too much with those noble gases. So this collection of like 17 elements are really all that we see in living systems. Now we have a few, like there's iron in our blood. There is some zinc and manganese sometimes is needed in very, very small amounts. And these are called trace elements. But for most of our organic molecules, which we're going to see in the third section of biochemistry, it really is just 4 major atoms. Carbon, or sorry, I have a little mnemonic here. Hydrogen, oxygen, nitrogen, and carbon. It spells honk, right? So hydrogen is element number 1, oxygen is element number 8, nitrogen is element number 7, and carbon is element number 6. Like 94% of all biological molecules are made up of just these 4 atoms. So when we talk about carbohydrates and proteins and lipids and nucleic acids, they're almost all just carbon, hydrogen, oxygen, and nitrogen, with a little bit of these other things kind of scattered around. So that's really where we're going to be focusing on with these elements. And that's about it for the periodic table. So there's rules and things. So if you've taken a chemistry class, you might remember some of those things, which is great, but we're just not going to dive into a lot of that detail. But do know that these 4 elements make up most of our biological molecules. So we're going to take a look at what is an atom. So each one of those elements is represented by a particular atom. So atoms have 3 major parts. We have protons, neutrons, and electrons. These are called subatomic particles. And then structurally, they have a nucleus. And just like a cell has a nucleus just means center of something. So the nucleus is where we have protons and neutrons, and hovering, orbiting, clouding, whatever planet or whatever model that you want to use, electrons are outside of the nucleus. So in our diagram here of helium, the red is the protons, the yellow is the neutrons, and those are found in the helium nucleus, and the black are the electrons, and they're found orbiting around the outside. So we can do what's called a planetary model. So it kind of looks like the sun's in the center with the planets going around, like our solar system. Or probably a more realistic representation is the negative charge of those electrons are just kind of hovering in a cloud around the nucleus. And this is what's called the orbital model. Not super concerned about that, but just know protons and neutrons are in the nucleus. Electrons are in the outside of the nucleus. They're orbiting, they're outside in that space. All right. Some other important characteristics that we need to know about protons, neutrons, and electrons is their mass and their charge. Okay? So mass is, right, their matter. They have mass. How much do they weigh? You can think of that. And then we have charge. Do they have an electrical charge? And if so, what is it? So protons have a mass of 1 atomic mass unit, right? So that's really nice. Neutrons have a mass of 1 atomic unit. And electrons, they do have mass, but for our purposes, very just general basic chemistry, our electrons, we're going to say, have no mass. Okay? They do, but it's so negligible, it's not going to impact what we're going to talk about. And then for charge, protons have a +1 charge. Neutrons are neutral, that's That's why they're named that. They're neutral. And electrons have a -1 charge. So that's kind of what these protons with a plus, neutrons with a 0, electrons with a negative, showing that they have their charges. Okay. So those are some characteristics of these subatomic particles. Protons are found in the nucleus. They have 1 atomic mass and they have a +1 charge. Neutrons are found in the nucleus. They have 1 atomic mass and no charge. Electrons are found outside of the nucleus. They have no mass and a -1 charge. Okay. It is really, the mass isn't super concerning for us because we're not going to be doing like chemical reactions and having to solve for mass. It's the electrons that are going to be more important for us because they are what's involved in the bonding of things. And we're going to be dealing with bonds, molecules that are bonding or losing electrons or sharing electrons. So when we are identifying elements, we identify them, we kind of name them or give them their characteristics based on their number of protons in the nucleus and the electrons that are orbiting around the nucleus. So if we go back, I can't go back on my PowerPoint, but if you're looking at the periodic table, you'll notice that they are, let's see. Oh yeah, good, okay. I have this slide, I forgot I had this slide. So when we talk about all of the little boxes on the periodic table, there's numbers associated with the symbols. The symbols just are like shorthand for what it is. So C for carbon, Na for sodium, O for oxygen, H for hydrogen. So that's our atomic symbol. The atomic number equals your number of protons. Okay, so that gives the identity. There's no two elements that have the same atomic number. They're just, every element has its own atomic number, and that number equals the number of protons that it has in the nucleus. And the atomic weight, or atomic mass sometimes, is protons plus neutrons, because remember, they're the only ones that have mass. So you add those together, and that gives your atomic weight. So for carbon, it has 6 protons, 6 neutrons, and has 6 electrons. So protons make it carbon. Carbon is number 6. You add your protons and neutrons together, you get your atomic weight, which is 12. Okay, so that's just the characteristics of carbon. We can do the same thing for sodium. Sodium is going to have 11 protons. And you're in a neutral atom, your electrons are always going to equal your protons. So it's going to have 11 electrons. And if we take a look at the mass, we'll round up to 23. So if it's got a 23 mass, but only 11 protons, we can deduce or calculate the number of neutrons. We just take 23 minus 11 gives you what, 12? 12 neutrons. So your neutrons don't always have to equal your protons. Protons and electrons do for neutral atoms. Atomic mass, usually you can have more neutrons, more or less neutrons than protons, but that only affects the mass. It doesn't affect the identity of the element. The number of protons gives you the identity. If you change the number of protons, you change the atom. It's no longer going to be the same. So if we were to take carbon and add 2 protons, it's no longer carbon, it would be oxygen, but we can't do that. Chemistry doesn't, that's like atomic nuclear reactions if we're going to add protons and stuff. When we do have something with more or different levels of neutrons, because the neutrons don't affect the chemical reactivity, that's just the electrons. Neutrons don't affect the identity, that's just protons. Neutrons affect the mass. And when we have elements that have varying numbers of neutrons, we call those isotopes. Okay? So here I've shown some different types of isotopes. So hydrogen is a weird atom because it just has 1 proton and 1 neutron. It doesn't even have a neutron. 1 proton and 1 electron. It doesn't have a neutron. But there are some types of hydrogen that do. So this is called deuterium and tritium. These are hydrogen isotopes. They're still hydrogen because they have the 1 proton and the 1 electron. But these isotopes, deuterium and tritium, have a little bit more mass because they have more neutrons than our typical hydrogen atom. All right, look. Okay, talked about that. Moving on. Okay, so the next thing the book talks about is molecules and compounds. and what's the difference. I'm not super concerned about knowing exactly what the difference is. Just understand molecules and compounds are combinations of atoms that are bonded together. So they're usually going to be covalently bonded. We haven't covered covalent bonds yet, but see, we have, this would be H2. We have 2 hydrogen atoms hooked together. This is O2. We have 2 oxygens hooked together. Here's an N2. 2 nitrogens hooked together. This is water. 2 hydrogens and oxygen. This is carbon dioxide. This is methane. And I don't know what that is, but it's a lot. It's a bigger molecule. Some nitrogen containing compound. I don't remember. It's just a kind of a cool picture. Molecules and compounds are the combination of atoms in certain relationships, sometimes ratios, that have different functions than the single atoms all by themselves. So water behaves completely differently than hydrogen all by itself or oxygen all by itself. Carbon dioxide is completely different than oxygen all by itself and carbon all by itself. All right, so now we can take a look at the bonding and reactions. So when we take a look at how atoms interact, we're really just looking at the electrons. The protons and neutrons are center of the atom. They're in the nucleus. They don't really interact with other atoms. They just give identity, right? So the protons just give the identity. The neutrons help with mass. It's really the outer layer of electrons that can bump into other atoms and interact. There are some rules when it comes to those outer electrons. You may have heard of this word before. They're called valence. Valence electrons. Valence just means the outer shell. Okay. In the first 20 elements that we are looking at, before it starts getting really weird, if you're to go into general chemistry, we have some rules. So there are what are called shells, valence shells, electron shells. And a lot of times in the planetary models, you'll see like the nucleus, and you'll see these rings of electrons, right? Kind of what we see in the picture here. In this first ring, this is our first shell, it can hold 2 electrons, and that's it. So that first shell, it's called the S shell. Again, if you've had chemistry, that might be coming back to you. In this second and all the other subsequent shells, they can hold up to 8 electrons. Okay. So when we talk about atoms bumping into each other and maybe reacting or not reacting, what we're looking for is how full is that outermost shell. If the outermost shell is just that first shell, like here in the helium atom, if it has those 2 electrons, so this is its limit, if it has 2 electrons, it's happy. That's what it wants. That's its limit. Any other shell, it's looking to fill that outer shell with 8 electrons. So helium is happy. Neon is happy because if we look at its outermost shell, it has 8 electrons. It's not going to react with anything else because it doesn't need electrons. It doesn't need to give away any electrons. It doesn't need to borrow any electrons. It doesn't need to share any electrons. It's good. So these are called chemically inert elements, and they're all listed on that far right-hand side of the periodic table. So helium, neon, argon, radon, all of those what are called noble gases or inert gases. But everybody else does not have filled valence shells. So hydrogen, I don't want to give emotions to elements. I don't know if they'd be sad, but they're not fulfilled. Their valence shells are not complete. So hydrogen is missing 1 electron to make it happy. Carbon is missing 4 electrons. It has 4 electrons in its valence shell, which means it needs 4 more in some way or another. Oxygen, 1, 2, 3, 4, 5, 6. It's missing or could use 2 electrons, and sodium only has 1 in its valence shell. So it needs 7 more. Or another way to look at it, if you have only 1 or 2 electrons in your outermost shell, you can actually give that one away and remove the outermost shell and then go back to this one, which has 8, and then it's happy. Okay? And this is when we're going to start taking a look at ions, and we'll see that when we take a look at ionic bonds. So any atom that is incomplete in its valence shell has the opportunity to react and make bonds with other atoms that are also incomplete in their valence shell. So those noble gases on the far right-hand side of the periodic table, we're not going to see those in molecules and compounds. It's everybody else, mainly again, hydrogen, oxygen, nitrogen, carbon, HONC, for organic molecules, that we're going to see those relationships in either sharing electrons or swapping electrons. So let's take a look at one way that atoms can reach that happy state, that fulfilled state of their valence shell. So the first one we're going to take a look at is called ionic bonds. And this is a reaction between a sodium atom and a chlorine atom. Now, if we take a look, sodium only has 1 electron in its valence shell, this guy right here. Okay? If we take a look at chlorine, it has 1, 2, 3, 4, 5, 6, 7. So sodium needs 7, or it needs to get rid of 1, and chlorine needs 1, or it needs to get rid of 7 to go back to the next lower shell that is completely filled. So in this case, when a sodium atom comes close to a chlorine atom, what actually happens is that sodium electron, the electron on that outermost shell of the sodium, pops off and it becomes a sodium ion, right? Look, now it has 1, 2, 3, 4, 5, 6, 7, 8. It is now chemically stable because it has a valence shell of 8. And then if we take a look at chlorine, because it accepted sodium's electron, 1, 2, 3, 4, 5, 6, 7, 8, it is also now chemically satisfied and fulfilled because its valence shell now has 8 in it. So what makes the bond? Well, we have to do some calculations of our new atoms. They're not really called atoms anymore, they're called ions. And the reason why is sodium has 11 protons, and chlorine has 17 protons. They're always going to have those. That doesn't change. But remember, protons are positively charged. Now, the electrons, sodium just gave away an electron that started with 11 electrons. It gave one away, and now it only has 10 electrons. So the overall charge, if we subtract 11 positive charges minus 10 negative charges, we have a net charge of +1. That makes sodium a positively charged ion. Okay? Chlorine had 17 protons, always has 17 protons, has 17 electrons, but it gained 1. So it now has 18 electrons. So what is its net overall charge? You have 17 positives and 18 negatives. You have 1 more negative charge, so it becomes a negatively charged ion. So now we have a positively charged sodium ion coming into close contact with a negatively charged chlorine ion. And what do we know about opposites just in the world around us? Opposites attract. So the sodium is attracted to the chlorine. Sodium ion is attracted to the chlorine ion. This is what we call an ionic bond. So whenever we have an atom losing an electron and another atom gaining the electron to create these oppositely charged ions, and then they come together and attract, this is called ionic bonding. Okay, it's one of the ways that these atoms can fulfill that valence shell. So they actually donate and gain electrons and then are attracted via those opposite charges. Okay. The next example of how some atoms can fulfill that shell is not by donating and receiving electrons, but sharing electrons. Co, meaning share, and valent means they're sharing their valence electrons. So here's a few examples, some hydrogen, oxygen, and methane. So hydrogen has 1 electron. Oops, I'll try to use the same color I did before. So it's got 1 electron, and remember that first shell needs 2. So hydrogen atom is short 1 for its happy state, its fulfilled state. So if we have 2 hydrogen atoms, each with 1 electron in their valence shell, they can actually share those electrons, right? So now there's 2 electrons. So this hydrogen nucleus says, hey, I've got the energy of 2 electrons around my nucleus. And this hydrogen is saying, hey, I've got the charge of these 2 electrons around my nucleus. We're both happy. So this is sharing electrons as your covalent bonds. Okay? And this is sometimes drawn, like hydrogen with a line to another hydrogen. This line is a single covalent bond. Oops, I spelled covalent wrong. Single covalent bond, okay? But if we take a look at oxygen, each oxygen has 1, 2, 3, 4, 5, 6 electrons in its valence shell. So it needs 2 more. So if you have 2 oxygen atoms come together, each one sharing 2 of its valence electrons, if we were to take a look at if everybody's happy, 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's happy. 1, 2, 3, 4, 5, 6, 7, 8. So each oxygen nucleus feels satisfied because they have 8 electrons in their valence shell. This is a double bond, so it's usually drawn like this. So this is a double covalent bond. So you might see that in some drawings as well. When there's 2 lines, there's 4 electrons being shared. When there's 1 line, it's just 2 electrons being shared. Now, these are of the same element, so hydrogen gas, oxygen gas. What do we have different atoms or different elements? We have carbon and hydrogen, say. So hydrogen, remember, it has 1. Carbon has 4 valence electrons, so it needs 4 to fulfill its outer shell. So if each hydrogen needs 1 and carbon needs 4, maybe we can make something work out here. So in this case, each hydrogen nucleus is happy because they have the energy of those 2 electrons around its nucleus. Yay! When we take a look, is carbon happy? Let's take a look. 1, 2, 3, 4, 5, 6, 7, 8 electrons in its valence shell. Yes, it is happy. And we can represent this in a couple ways. We can draw it like this, kind of with each one of those single lines representing a covalent bond, or we can draw it like this, kind of this chemical molecular formula. CH4 tells you there's 1 carbon and 4 hydrogens bonded to it. All right, so we have ionic bonds where we're swapping electrons to fulfill octets and attracted by opposite charges, or we have covalent bonds where the atoms come close proximity and they share the electric charge of those electrons to fulfill the octet. Okay. The last type of bond we're going to take a look at isn't a true bond necessarily. It's not swapping electrons or sharing electrons. It's more of an attraction of partial charges. So when we have atoms that are sharing electrons, sometimes they don't share equally. So carbon dioxide is equal. That carbon in the middle is sharing the electrons and the oxygen totally equal. They went to kindergarten. They know how to share. Water, on the other hand, doesn't share those electrons very well. Those electrons are mainly found, I'm going to make it really exaggerated. So most of those electrons, the negative charges, are going to be hovering around the nucleus of the oxygen because it's a bigger atom. And really all that's left out here is the single protons of the nucleus of the hydrogen. So what we end up with is a molecule that has one side that's a little bit more negative and one side that's a little bit more positive. And that's what these symbols mean. Partial positive and partial negative charges. So when you get some water molecules next to each other and you have the partial negative charge of the oxygen of the molecule here and a partial positive of the hydrogen here, there's a little bit of an attraction between that. And this is what we call a hydrogen bond. It's just the attraction of those partial charges between a partially positive hydrogen side and a partially negative oxygen side. But what's cool about these hydrogen bonds is it gives water very special features. Some of them you might notice, this is called surface tension. Like if you've ever seen an insect, kind of a water skipper, you have the bug sitting on the surface of water, not because it's magic, but because you have like this net of water molecules with all of these hydrogen bonds that the insect is so light, its mass is not strong enough to break those hydrogen bonds. Or sometimes you see water beading up, like these beads of water on the leaf. They're holding themselves together because of the hydrogen bonds, and it gives water some very peculiar characteristics. All right, and then lastly, just a quick rundown of how some chemicals can react with each other in these different patterns. So we have, let me take a look. We have a synthesis reaction. These aren't labeled, so I'll write that up here. Synthesis means to make, to synthesize. So if you have individual amino acids, like these little orange circles, and you add them together, you can make or synthesize a protein molecule. So in very basic forms, if you have element A, add it to element B, you have a brand new element called AB. So that's called synthesis reaction. The next type is called decomposition. Like to decompose, to break down. So here we have glycogen, which is this big green, it's a whole bunch of glucose molecules hooked together. If you start breaking those bonds, you're going to release the individual atoms. So that would be like if you had molecule CD, it went through a decomposition reaction and you've separated the individual component parts into C plus D. Okay. And the last one is called exchange reaction. Exchange reactions are where the two parts of the molecule kind of swap places. So here we have glucose and ATP. And what's going to happen is this phosphate group is going to swap positions and go in and hook onto the glucose. So here we have glucose phosphate, and now we have a diphosphate. There's only 3 phosphate groups. So that would be like molecule AB and molecule CD becoming AD and CB. They swap partners, break bonds and make bonds. So that's an exchange reaction. All right, so that wraps up our basic chemistry, atomic structure, chemical bonds, and a little bit of reaction. Our last video for chapter 2 is going to cover biochemistry, which is going to focus mainly on the molecules that are important in living things. So I'll see you next time. Bye.